Hello student, good morning. I am Dr.A.K.Sinha, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing solid state and under that I was discussing types of structures possessed by simple ionic compounds AB type. Only in that I was discussing main features of NaCl type structure. Actually under AB type structure, rock salt type structure is there. Second, cesium chloride type structure, and third, zinc blend type structure. These three, out of these three, two I have discussed. Now I will continue from zinc blends ZNS type structure. Already I have finished gaseous structure. Gaseous phase I have discussed. Liquid phase I have discussed. Now solid states I am discussing. Now under the solid state I will continue, that is the types of structures possessed by simple ionic compounds AB type. Under that now I will continue from ZNS type structure, also called zinc blend structure. Main feature of zinc blend type structure. First, its feature is it has FCC arrangement of S2 minus, means sulfur ions. This is the first feature. Second, Zn2 plus and S2 minus. Zn2 plus and sulfur ion, means S2 minus ions have 4:4 coordination tetrahedrally. 4:4 coordination. This is the second main feature. Example is CuCl, CuBr, CuIe, AgIe, BES. These are the examples of ZNS type structure. Again I am telling you, first its main feature, it has FCC arrangement of sulfur 2 minus ions, S2 minus ions, 2 minus. Second, Zn2 plus and sulfur 2 minus ions have 4:4 coordination tetrahedrally. Examples. First example is CuCl. Second, CuBr. Third, CuIe. Fourth, AgIe. And fifth, BES, barium sulfide. Now, structures of ionic compounds of the type AB2. First is calcium fluoride, CaF2 type. Calcium fluoride, CaF2 type. What are its characteristics? Now I am telling you. It has CCP oblique FCC arrangement of calcium ions. Second, calcium ion and fluoride ions have 8:4 coordination. Antifluoride structure. Antifluoride structure. Example is Na2O, where Na plus 1 plus and O2 oxygen 2 minus O2 minus ions have 4:8 coordination. Structure of ionic compounds of the type AB2. Again I am telling you AB2. Then calcium fluoride is the best example. Calcium fluoride type. Calcium fluoride type CaF2 type. Then its first characteristic is it has a CCP/FCC arrangement of Ca2 plus ions. Second, Ca2 plus and F minus ions have 8:4 coordination. Now, antifluoride structure. Na2O, where Na plus and O2 minus ions have 4:8 coordination. All things we have to remember. Okay. Now, types of close packed structure. Types of close packed structure. Here you can see that NaCl, that is, it has 6 coordination. Actually, for that, NaCl and cesium chloride. Cesium chloride, see, both looks same type of structure, NaCl and CHCl. But here coordination is different. In NaCl, it is a 6:6 coordination. But cesium chloride, CHCl, it is 8:8 coordination. 8:8 coordination. This is the difference. And if you will apply pressure, maintaining temperature 760 K, then 6:6 can be converted to 8:8, and 8:8 will convert to 6:6 coordination. Means on applying pressure and temperature 760 K, then NaCl can take the structure of CHCl, cesium chloride, means 6:6 coordination will become 8:8 coordination, and cesium chloride, which is 8:8 coordination, that will come to 6:6 coordination. Now next point, types of close packed structure. Types of close packed structure. There are 3 ways in which atoms in a crystals are packed. First is hexagonal close packing. In shortcut it is called HCP. Small h, small c, small p, HCP. Hexagonal close packing means AB pattern, AB dot pattern. Example, that is the beryllium, Be. Second example is magnesium, Mg. Third, calcium. Fourth, chromium. Fifth, molybdenum. Fifth, vanadium. Sixth, Zn. In all these metal, these are in hexagonal, or you can tell these metals are hexagonal packing, HCP. These beryllium, magnesium, calcium, chromium, molybdenum, vanadium, zinc have hexagonal close packing, HCP, or you can tell A, B, like that pattern. A, B, A, B, A, B. This type of pattern is going on in all these elements. That is the beryllium, magnesium, calcium, chromium, molybdenum, vanadium, zinc. Now, next is a cubic close packing, CCP. Cubic close packing, CCP. And here, what are the pattern? Then A, B, C. Again A, B, C. Again A, B, C pattern. Then these are found in iron, Fe, copper, silver, auric, platinum, aluminum, nickel. In all these elements, cubic close packing is found. Means its pattern is A, B, C, A, B, C, A, B, C, like this. This is the pattern. And these are found in iron, means Fe, Cu, means copper, Ag, silver, Au, gold, Pt, platinum, Al, aluminum, and Ni, nickel. In these elements or in these metals, CCP structure is found, cubic close packing. Now, again you listen. Space occupied is equal to 74%. Space occupied is equal to 74%. And space unoccupied, that is 26%. Okay, you remember, space occupied is 74%. Space unoccupied is equal to 26%. The space occupied by sharing in one layer of the hexagonal close packing is 60.4%. Okay, again you listen. The space occupied by spheres in one layer of the hexagonal close packing is 60.4%. But in cubic close packing, space occupied is 74% and space unoccupied is 26%. Correct? And space occupied by a sphere in one layer of the hexagonal close packing is 60.4%. Now come to the body centered cubic, BCC. Body centered cubic, BCC. Example, in alkali metals. Alkali metals, it will start from the lithium, sodium, potassium. These are the alkali metals. Then body centered cubic, that is the BCC. It is found in alkali metals, and this space occupied is 68% and empty space is 32%. Question is asked. This value you have to remember. Okay. Body centered cubic, that is the BCC. Example in alkali metals. Alkali metals examples, lithium, sodium, potassium, like that way. Cesium also you can tell. Then space occupied is 68%. Empty space is 32%. This is not a close packed arrangement. You remember. Body centered cubic, BCC. This is not a close packed arrangement. Now next point, tetrahedral void. Tetrahedral void. What is the tetrahedral void? It is a triangular void surrounded by 4 spheres arranged tetrahedrally around it. It is a triangular void surrounded by 4 spheres. If we will take 4 spheres, then inside the 4 spheres you will find a triangular void. It is a triangular void surrounded by 4 spheres arranged tetrahedrally around it. Now, octahedral void. What is the octahedral void? It is a combination of 2 triangular voids surrounded by 6 spheres. Surrounded by 6 spheres. Octahedral void I am telling now. It is a combination of 2 triangular voids. Combination of 2 triangular voids surrounded by 6 spheres. Now, next point. Actually, I am reviewing the chapter. Okay, I am reviewing the chapter solid state. Now, come to the radii of the voids in terms of radii of packing sphere. Packing sphere. Its radii is capital R. Radii of voids. Radii of the voids in terms of radii of packing sphere. According to the radii of packing sphere, what is the radii of the voids? That I am telling. That is called radii of the voids. Radii of the voids in terms of radii of packing sphere. Radius R. Radius R, small r, of the tetrahedral void. Radius R, small r of the tetrahedral void is equal to 0.225 r. Here r is capital R. That is the packing sphere radius. Then radius r, that is for related to void. Radius r of the tetrahedral void is equal to 0.225 r, capital R. Correct? Now, same way, radii means a small r of the octahedral void. Then in terms of capital R, what is its value? Then 0.414 r. Then see how a small r is related to capital R. A small r is the radii of the octahedral void. Correct? Then for both I told you, for tetrahedral void, what is the small r? That is a small r of the tetrahedral void means radius of the tetrahedral void is equal to, in terms of capital R, it is 0.225 r. And for the octahedral void, a small r value is equal to 0.414 capital R. Now, next term, that is the number of voids in terms of number of atoms. Question is asked in examination. Number of voids in terms of number of atoms. Then number of octahedral voids in terms of atom, I am telling you, number of octahedral voids, that is equal to number of atoms in the close packed arrangement. Number of octahedral voids is equal to number of atoms in the close packed arrangement. Now, in case of tetrahedral voids, number of tetrahedral voids is equal to double of the number of atoms. Number of tetrahedral voids is equal to 2 into number of atoms, or you can tell octahedral voids. Again I am telling you, number of octahedral voids is equal to number of atoms in the closed packed arrangement, and number of tetrahedral voids is equal to 2 into number of atoms or octahedral voids. Now next points I am telling, all noble gases have CCP structure except helium, which has HCP structure. Question is asked, all noble gases have CCP structure. Exception is helium. Helium has HCP structure, hexagonal closed packing structure. But all other noble gases have CCP structure, cubic closed packing structure. Now next point I am discussing about ferrites. Ferrites, F-E-R-R-I-T-E-S, ferrites. Ferrites are the compounds with formula AFE2O4, where A is a covalent cation, such as Zn2+, Mg2+, etc. Again I am telling you, ferrites. Ferrites are the compounds with formula capital A Fe2O4, where capital A is a divalent cation, such as Zn2+, magnesium2+, etc. They have a spinal structure. Ferrites have a spinal structure. A spinal is the mineral. What is formula? MgAl2O4. Same formula what I told you, AF2O4, where A is a divalent cation, such as Zn2+, Mg2+. Then I told you these have a spinal structure. AF2O4 has a spinal structure. A spinal is the mineral. What mineral? Which mineral? MgAl2O4. Now, what is the radius ratio? Next term, radius ratio. Then by name it is clear. Radius ratio. Then ratio of cation divided by radius of anion. That is called radius ratio. That is the radius ratio. Radius ratio is equal to radius of cation divided by radius of anion. That you can tell a small r plus divided by a small r minus. A small r is the radius. R plus means for cation, r minus means for anion. Now, next term I am talking about relationship between radius ratio, coordination number, and structural arrangement. Question is asked, and so listen carefully. Relation between three means relation between radius ratio, coordination number, and structural arrangement. Then radius ratio, I am telling you that actually there is a range. There is a range means radius ratio between 0.155 to 0.255. This is the one range of radius ratio. Second range is from 0.225 to 0.4141. This is the second, you can say, range of radius ratio. Third range is 0.414 to 0.732. This is the third range of radius ratio. And last range is 0.732 to 1. 0.732 to 1.000, like that you can tell, or simply 1. Then you have seen here, it is in continuation. First range is starting from 0.155 to 0.255. Second, you will start from 0.255 to 0.414. Again, third, it will start from 0.414 to 0.732. And again, it will continue from 0.732 to 1. Correct? 4 range is there for the radius ratio. Then for first radius ratio, what will be the coordination number for the first radius ratio? Means for 0.155 to 0.255, its coordination number will be 3. You remember, coordination number will be 3, and structure arrangement will be planar structure. If 3 coordination is there, then obviously it will form triangle. 3 point means triangle. Okay. Now next range, second range, 0.225 to 0.4141. Its coordination number is 4. Then 4 means tetrahedral. 4 means tetrahedral structure, tetrahedral arrangement. Now third range, now it will start from 0.414 to 0.732. Its coordination number is 6. Then 6 means, 6 means octahedral. Octahedral. Now last, starting from 0.732 to 1. Its coordination number is 8. 8. Then 8 means body-centered cubic. Body-centered cubic. Now next relationship I am going to discuss. Relationship between the nearest neighbor distance, d, small d, and the age, Iitjee, age, means a small a, of the unit cell. Okay. The relationship between the nearest neighbor distance, that is a small d, and the age, a small a, of the unit cell, I am discussing. Then for the simple, d is equal to, a small d is equal to a small a, b, c, already told you, that is on x-axis, on x-axis length, on y-axis length, and on z-axis length. Okay. Then here, when neighbor distance, nearest neighbor distance, if it is d, a small d, then that d will be equal to a length on the x-axis, a. Then when d is equal to a, then what will be the body-centered d? What will be the body-centered d, a small d? Then it will be under root 3 divided by 2. Okay. D value, a small d value will be under root 3 divided by 2 into a small a. Correct? A means, I told you, on x-axis length, a. Cubic cell, unit cell, its length will be a small a. Then d is equal to under root 3 divided by 2 upside a. Means after putting the value of root 3, 1.732 divided by 2 into a, you will get 0.866 into A. You remember this relation. In case of D is equal to A, D will become under root 3 divided by 2 into A. After putting the value of root 3, you will get 0.866 A. And for the face centered, what is the value of D? For the face center, then 1 upon root 2A. 1 upon root 2A. Then after putting the value of root 2, 1.414, then you will get D is equal to 0.707A. Means D is equal to 0.70A. Okay. It is a half of the face diagonal. It's why this value is, it is a half of the face diagonal. That is a root 2 divided by 2 into A. A is upside. It is a half of the face diagonal. Half. That is root 2A divided by 2. Correct? Then now I am stopping only here. Actually further relation is also there. That I will discuss next class. Many terms are there. I will discuss next class. All points what I am discussing, all are very, very important, and these are in very simplified way. And these questions are asked because I am reviewing the chapter solid state. That's why I am briefing all, you can say, important terms. Thank you.